All right, now let's check out what's known as a solenoid and a toroid. These are very common configurations of current carrying wires. A solenoid you can think of as a large collection of loops of wire, and the difference essentially between a solenoid and just loops of wire is that the solenoid typically is much longer than it is in diameter. And so first we're going to look at a solenoid. So I've got this picture from the book where on the left you've got sort of the physical setup for the solenoid, and now we've got on the right a cross-sectional cut through the solenoid so that you can see on the right-hand side the current going into the page, and then those loops loop around back to the left-hand side where the current's coming out of the page. And what we want to try to figure out is what's the magnetic field inside the solenoid, so inside the tube of current loops. And so first we're going to start off with the Biot-Savart treatment, and then at the end I'm going to show you that using Ampere's law you get the exact same result in a much shorter manner. So first thing, if we start with Biot-Savart, then we basically have a bunch of loops of current. And if you remember back to our work deriving the expression for the magnetic field along the central axis due to a loop of current, you get this expression. And here, instead of calling it B, I'm calling it dB because I've actually got a bunch of loops here, right? And so that dI value, how much current, dI is equal to, if you look at our picture, dI is equal to the number of loops, n, divided by the length, multiplied by the current running through each of the loops, and then multiplied by dy, the little chunk of height, if you will, of the solenoid. And so I'm going to substitute that in, and I get this more, slightly more complicated expression where the contribution to the magnetic field from each small dy chunk of loops in the solenoid is this expression. And so what I want to do now is I want to integrate the expression because I want to add up all of the contributions. And just like with the single loop, notice that the magnetic field here is directed along the j-hat direction. This is because the solenoid in this problem is aligned along the y-axis. And so from the figure, so if you look at the figure here, sine theta, so here's theta, here is theta. Try it one more time. Here's theta. And if you look at this triangle here, sine of theta then has to equal y over the square root of y squared plus big R squared, where big R is the radius of the solenoid. And so I can take the derivative of both sides with respect to y. On the left-hand side, you'll notice that it's sine theta. So when you take the derivative with respect to y, you actually get cosine theta and then d theta dy. That's the chain rule. And on the right-hand side, you can take the derivative, and I've already done all the work for you, but you can follow along there if you do the product rule or the quotient rule, depending on what you like to do for your integral or for your derivatives, and then simplify. You end up getting this expression over here at the end. That's what d dy of the right-hand side of this expression is equal to. And so that means we can rewrite sine theta equals y over the square root of y squared plus big R squared as this expression. And the reason we want to do that is because if you look at this expression up here, you have all of those terms in that expression, and so I'm going to substitute out for r squared over y squared plus big R squared to the 3 halves dy. I'm going to substitute in cosine theta d theta. And if you look at the picture here, theta is going to be, when we go to do the integral, theta is going to range from theta 1 and theta 2 here, sort of depending where you are on the central axis. Those angles will be whatever the angle needs to be to get to the end of the solenoid. And so, and just keep going here. So when I substitute that in, I now have this expression that I need to integrate, and that's actually a pretty simple integral. And so I end up with this expression for a finite solenoid. And if I allow the solenoid to be infinitely long, or in practice, if the length is significantly larger than the radius, then the solenoid, the field inside the solenoid, is equal to mu naught I n over L. And that often would get written like this, and I believe it's done like this in the book, mu naught little n I, where little n is the loop density. So that's n, the number of loops, divided by L, the length of the loop. So that is the magnetic field inside a solenoid. You'll notice something interesting. There is no there's no R value in any of these expressions, right? They're all the same expression, but R isn't present there. So the solenoid field does not depend on the size of the loops. It depends on how many loops there are, how many turns, what the current is through those loops, and essentially the length of the solenoid. And so, so if you want to generate a uniform magnetic field, then a solenoid is the configuration that you would choose to accomplish that. Now, before we move on to the toroid, I just want to show you that we could come up with this same expression using Ampere's law. And so if we were to use Ampere's law, what we'd want to do is we want to draw an Amperian loop and then leverage the Ampere's law. So let's pick a couple loops to look at here. First, let's pick this loop to look at. All right, so there's my Amperian loop, and we know that if you do this integral, it's got to equal mu naught over I enclosed. And so in this case, I enclosed is equal to, well, whatever the current is in the wire. And then, let's see, we've got 1, 2, 3, so 4 loops. So I times n, the number of loops in the wire, divided by L, the length of the solenoid, and then multiplied by x, which in this case would be my 4 loops. So this x I'm just going to use as a generic placeholder, but in this case it would be 4. And so this is, I'm just going to write it with little n, that's the density, and then times x, how many loops. And so on the left-hand side, B, so what is B equal to in these different regions? Well, in here, we are the same distance away from these current carrying wires, and so B is going to be constant. And so, and this is going to be, the length there is my length x. So this length x. So that's this portion of the path integral. And then what about this portion? Well, this portion is going to contribute 0. What about this portion of the path integral? Also going to contribute 0. And what about out here? Well, I tried to draw it this way, but it was kind of difficult because I ran out of space. But if I extend this out far enough, if I get far enough away from the wires, then I think it's reasonable to say, well, then the B field must be 0 if you get further and further away. And so that contribution is going to be 0. And so then you end up with the B field inside the solenoid is mu naught I, or mu naught little n I, which, if you look down here, you get is the expression that we came up with earlier on. And so using Ampere's law, you can immediately come up with that expression that we derived using Biot-Savart. All right, so following up the solenoid, what about a toroid? Well, toroid is if you took the solenoid and you took the ends and you bent the solenoid into a circle and connected the ends. All right, so this is the idea of a toroid. And if we use Ampere's law outside of the toroid, so this would be, say, in this figure D, if you draw your Amperian loop inside the hole, or outside, then the current enclosed is 0. For D1, it's obvious that there's no current enclosed. And for D3, it looks like there's current enclosed, but it turns out that there's the same amount of current coming out of the page as there is going into the page, and so that means that the net enclosed current is 0. So that leaves us with just inside the toroid, so inside the loops. And so if we use Ampere's law, let's say we're going on path D2 here in the picture, you can see that. Well, then you simply have a constant B field. The path length is 2 pi r, and then rearranging the terms, you get that the magnetic field inside the toroid is mu naught n I, so n being the number of loops, divided by 2 pi r. And so what this tells you is actually that the magnetic field is not uniform inside the toroid. It actually changes as you go from the inner radius of the toroid to the outer radius. But if the radius of the toroid is much larger than the radius of the individual loop, so that's to say, in this picture over here, if the radius of the toroid is much, much larger than the radius of the individual loops, and so that's what we've got written right here. If that's the case, then it turns out that you can replace the little r, the distance from the center, with big R, the actual radius of the toroid itself. And then the magnetic field inside the toroid is roughly constant. And it's given by this final expression here.